All right, so good afternoon, everybody. Today's paper is on, as Dr. Lin has mentioned, search-based software testing, but in a more unusual context. So in this case, it's generation of test cases for self-driving cars. Before we talk about the paper, we just talk a little bit about the authors. So there are 6 authors in total, spread out over a number of institutes in Sweden, all with interests in either ML or safety-based software engineering. Yeah, so just these are just the pictures of the authors and their research interests. So before we talk about the content of the paper, we need to discuss some background terms as well. So previously, in the previous paper discussion, I believe I've already covered the terms for search-based test case generation as well as the evolutionary algorithm. So we'll just skim over these. There are 2 new terms here are relevant only to this paper, which is the SVL simulator and the ego vehicle, which I'll discuss about later as well. So as I mentioned last time, so the search-based test case generation is just a search process that generates tests fulfilling various criteria. I'll explain more exactly about this in greater detail later on in the slides as well. And search-based test case generations usually use evolutionary algorithms. So these are algorithms use mechanisms inspired by biological evolution to solve the optimization problem that is the crux of the search-based test case generation. So one example of such evolutionary algorithms are genetic algorithms, which are typically used in SBST. Next, we'll talk about the SVL simulator. So in the context of self-driving cars, there's now software to simulate the action in self-driving cars, so you don't have to actually test them out in the field. So one such simulator is the SVL simulator developed by LG, which is used for simulating autonomous vehicles and it's for running simulation-based tests. So this is a bit dry, so I just have some pictures here to show how the simulator looks like. So the simulator can simulate a wide variety of situations. So we see some pedestrian situations here with some data here. Multiple car scenario as well as a single car on the road scenario, as well as a more abstract view of the scenario as well. And this is an example of a scenario used in testing the self-driving car. So here we see a more abstract view, which shows the route of the car as well as other objects in the path of the car. And here we see the standard view of the car as simulated. Finally, we talk about the ego vehicle. So the terminology in the paper often mentions an ego vehicle, which is essentially the vehicle under test or the vehicle is being controlled, just to separate it from other vehicles. So in the case where we have multi-vehicle simulation scenarios, we want to differentiate the vehicle that's being driven, self-driven, as opposed to other vehicles which are not being controlled. So it's just the term they use to indicate which vehicle is being controlled, which is the ego vehicle. So now we talk a little bit about the motivation for the paper. So we already have the concept of self-driving cars. It's not new in any stretch of the imagination, which is an AI system where the car can move itself around obstacles and pathfind and all that stuff. And next, however, the new recent innovations are virtual prototyping platforms for this car-based software. So as I mentioned before, this is the virtual software that lets us test the cars in the digital world without having to actually test them in the field. So of course, once you have the simulation platform, then we have simulation-based testing. But then of course, once you have simulation-based testing, what comes next? What's the next step that we want to take after we can test it? So this is the audience question. Does anyone want to try answering?
Yeah, and a volunteer. So the basic, maybe I can rephrase Darren's question. So for now, we have a virtual prototyping platform for anyway, we want to design a self-driving car systems. So the first step is that we want to have the simulation-based testing. And Darren, would you please more specific on what is simulation-based testing?
Yes, sure. So the idea behind simulation-based testing is that since we already have the platform that can simulate the action of the car, the self-driving car, we can also run scenarios that help to explore what happens under certain situations that we can't do in real life. So, for example, what happens when the car comes very close to pedestrians or very close to other cars? What will the self-driving software do in these scenarios?
Yeah, so that is basically the testing, right? Then the second step is, suppose we already have can such a way. That means that we can generate a lot of the corner cases, like the car is very close to the pedestrian, or sometimes there's a crash before the ego car. And Darren's question that what is the next step after we have those kind of scenarios, right, Darren?
Yeah, exactly that.
So maybe you can have a guess. Maybe I think people can comment and have a random guess. So suppose we have those exceptional corner case simulations. Once we have that, and what's supposed to do next? Anyone would like to have a try in this autonomous driving scenario? Then Darren, you can point a component here.
Yeah, sure. Maybe Eugene would like to try answering.
Okay. It's quite an open-ended question. So my guess would be that, well, we want to update the model to be able to pass the test, and then following that, deployment.
Maybe analysis of data.
Well, yeah, it's close, I guess. I guess it's kind of open-ended, so the question is quite difficult in that sense. So the idea was to bring in the concept that since we have a search-based software testing, so we have some pre-existing tests that can run on the simulation. So the next step would be to refine the test. So that's what the idea will be: simulation-based test case generation. Yeah, I understand it's quite open-ended, so it's not surprising if you can't get it either. I realize it's quite a difficult question in that sense. But yes,
but here, so the question is search-based testing or, sorry, the simulation-based test. Oh, okay. So maybe I raised a question here. Maybe my question is too early. Once we have the search-based testing, usually it means we model the problem into an optimization problem, right?
Yes.
So my question, maybe I raised it too early, is that what is optimization goal in these self-driving car scenarios?
Yeah, exactly. So that's also one of the key questions that the authors raise and answer in their paper as well. So I'll discuss it in more detail later. But yeah, that's one of the core questions when it comes to applying SBST as well. So what is the objective function and what is the search algorithm as well? Yeah, so these two will be answered later on as well. So to bring it back, so now that we have simulation-based testing, the next step is to automatically generate the test cases as well. So instead of having to think up test cases, we use algorithms to optimize test cases to expose more critical failures in the software. So what do we want in a test case? So we want a test case that can expose the bug in the software. So maybe you want to explore the behavior of the self-driving car under certain dangerous scenarios. Like what if the pedestrian comes very close? You want to make sure that the behavior is in line with maybe safety specifications or something similar. So you want these kind of test cases that can expose either bugs or violations of safety requirements in the self-driving software. And that's what we want to optimize for. So currently in terms of SBST, the current existing technique is just random testing, where we just randomly generate test case. So the authors propose a novel technique to improve this process, and hopefully this new technique will be better than just randomly generating test cases. So the approach is, as mentioned before, to use SBST to optimize the test cases to produce a violation of safety requirements. So this violation, for example, if you want to see it, what cases can cause the car to maybe hit a pedestrian, and then we can work around it and improve the software to make it better. So of course, we have to ask certain questions before we can even use the SBST process. So what would the test cases look like? So what is the structure or the representation of the test case? This is also important because then it will affect how we manipulate the test case. How to judge the quality of the test case. So in this case, this refers to the objective function. So how to score the test cases so we can tell which test cases are better, to choose them, to select them. And finally, what kind of algorithm we can use to evolve the test cases. So now that we have a representation of the test cases and we have an objective function, we need to know how to evolve the test cases so that we can continually update the test cases to be better. So we look at these three questions in turn. The first will be how the test cases look like. So for this, the authors propose using what they call a noise vector data structure. And before we talk about the noise vector, we'll talk about the basic representation of a scenario. So first, the authors use this tool called the SVL Visual Scenario Editor to generate a basic scenario first. So this is in this editor, they specify the agent. So in this case, pedestrians, vehicles, ego vehicles, which the self-driving software controls, and as positions in the map. And then they also specify the path they take as via waypoint. So they essentially map the way by reaching each waypoint, presumably in a straight line. And so they have a pre-existing map which they import first. They create a basic scenario. So the authors mentioned they only tried one basic scenario, which is that the eagle car moves towards the target and the pedestrian crosses the road from the right. After that, they export this test case, this scenario, to the SVL simulator, and then they manipulate this exported format to produce a new test case scenarios. So the test scenario is modeled in this format. You have several parameters. Each parameter has a range. So R sub I min and R sub I max is the max and min values possible for this parameter. And they convert this into a noise vector. So this is a representation they can use to manipulate. The reason why they do this is because it's easier to manipulate the normalized values because they don't have to have knowledge
So I
about.
understand there is a base scenario. So can you go back to the previous slide? The previous slide, yeah. So so my question here is that does all the evolution or search algorithms based on the same basic scenarios?
Yes, from what I can tell, yes, the authors only explored this one scenario.
And this basic scenario is manually defined by the expert.
They don't specify where the scenario came from. They just kind of put it there in the paper.
Yeah,
so
I just have a gut feeling that based on different basic scenarios, I think the search algorithms may be a little bit different. Am I right?
Yeah.
Right,
The authors mentioned that as the authors mentioned that as one of the possible threats to the validity of the paper, because they mentioned that you might have to change the format or the algorithm to.
Yes, because you can see that this basic scenario is very detailed. The eagle car moves toward the target, and the pedestrian cross the road. But what if the eagle car move the target, and there's some car driving ahead of the eagle car, or there's a car driving behind the eagle car? That what becomes a very different scenario, and based on the different scenarios, the presentation may look different. And the presentation is different, and the search algorithm will be different. So that means it has a problem of generalizability.
Yeah, and so it also mentioned about the threat to external validity later on in the paper as well.
Okay, keep going.
Yeah. So from this test scenario, they normalize the values and we get this noise vector with values normalized between -1 and +1. And the author also mentions a way to convert this noise vector back into a test scenario. So now we can kind of move back and forth between the generic representation for manipulation as well as the specific representation for use as a test case scenario. So now we have this idea of what the test cases will look like in terms of the representation of the test cases. So next question is, how do we judge the quality of the test case? So what kind of objective function do we use? So the authors specify 3 aspects that they want to optimize. The first is the total Euclidean distance. So Euclidean distance means here that we take the R2 norm, L2 norm essentially, the square root of the square of the Cartesian distance between each point. So this is the standard idea of distance, the standard constant distance that we are using in our 3D world. And we take the total Euclidean distance of the equal vehicle from non-equal traffic during the scenario execution. The next will be the total distance of the journey. So the authors don't give a justification for this, but they say that they want test cases to have a longer total distance in general. I suppose just to make it a more robust test case, because then you don't have cases where you have degenerate behavior occurring because of the short journey distance. And finally, the third aspect they want to optimize is the number of accidents. So given these 3 aspects that the authors want to optimize, the audience question is now, for these 3 aspects, which ones do the authors want to minimize and which ones do they want to maximize in order to make the test case the most optimized? So recall again that previously we talked about what makes a good test case, which is that the test case should expose a violation of safety requirements. So the more safety requirements are violated, the better the test case is. So with this information in mind, this quantity should be minimized and maximized to create the most so-called dangerous test case.
Yeah, and a volunteer would like to have a try. So during the scenario, if you want to construct a search. So basically, it means that maybe I can rephrase it a bit. So in the scenarios, the autonomous driving systems, the autonomous driving system will be respond to the environment, right? So what we can input into the autonomous system is actually the environment change. The car is driving, and the scenario is changing. Sometimes the pedestrian cross the road, and sometimes the vehicle happens before the car, or sometimes some car is chasing the evil vehicle. That is all possible, right? So whatever it is, we have a way to generate these scenarios, then Darren raised a question is that in order to make sure our environment can trigger the autonomous car into some accidents, and how do we maximize those three measurements? Right. So any volunteer would like to have a try. If no volunteer, Darren would like to point some students here.
Sure. Will we, Xianglin like to try?
So the question is, so sorry, I have phone call.
Oh, sure. Okay. In that case, maybe Xianglin would like to try?
I think Xianglin is preparing his slides.
Oh, okay.
Maybe you can.
Yeah, sorry about that. Yeah, I'm looking at my slides.
Oh, no problem. Maybe Alvin would like to try then?
Yeah, I'm back. So the question
okay.
is.
Yeah. So the question is that given these three aspects we discussed before, to make the test case expose the most safety violations, which of these three aspects, which one should we minimize, which one should we maximize?
Yeah, so maybe I can rephrase the question to Changshen. So basically, what we want to test is autonomous driving system. So that means the car is equipped with autonomous driving system. It's driving on the road, but of course, it's not driving on real road. It's driving in a simulated scenarios. So how do we maybe change the scenarios to make the autonomous system to have accidents, right? So basically, if we want to test it, we want to test it in a comprehensive way. We want to cover as many corner cases as possible. So in this case, so the question is that if we want to make the autonomous system to trigger the accident, to trigger the autonomous system into an accident, and how do we minimize or maximize the certain scenarios? For example, giving the total distance of the ego vehicle from the other vehicle, right? The non-ego traffic with the other vehicle during scenarios. Do we need to maximize or minimize their distance?
Yeah, and also these are three aspects of generated test cases, right? Yeah, for the I think first for the number of accidents, I think we want to maximize it because accidents are very rare in the training data, and but it's in the meantime it's very vital for the security of the autonomous driving system. This will be considered as a good corner case.
So it's a maximization problem, right? So in the first one or the second one, any idea about that?
But for the total distance of journey, I don't know. Yeah.
Okay, yeah. What about the last one? Do you want to try? What about the total distance of the ego vehicle from non-ego traffic?
Minimize.
Yeah, I have no idea. Yeah.
Oh yeah. I'm not sure who said that, but yeah, minimize.
I think Junbo suggests we should minimize the distance.
Yeah. Do you want to give a reason why?
Because we maximize, I think it does not make any sense. Like if two vehicles is far away from each other, then of course that's very safe situation, right?
Yeah, exactly that. So the closer the ego vehicle is to non-ego traffic, the more dangerous it is because you have higher chance of a collision or something. So exactly that. So we minimize the distance, we maximize the distance of the journey because we want to see longer test cases, more robust test cases in general. And of course, we maximize the number of accidents because accidents indicate failures in the vehicle behavior. So we want to see exactly how they fail, and we can use that to improve the vehicle behavior as well in the future. So yeah, this concept summarizes how the objective function will function. So this is the formal definition of the three aspects. So this is the ego distance, which just for every step, every waypoint, we just plot the distance between the ego vehicle position and the agent position, and we sum that in total, and that's the total distance between the ego vehicle from non-ego traffic.
Okay,
For the journey
so
distance,
the agent includes both pedestrian and other vehicle.
yes, pedestrians, other vehicles, I guess also objects in the map as well, things you can possibly collide into, I suppose.
Okay.
Then with the total distance is just, and understandably, just the distance, the starting position of ego car and the ending position of ego car, we just take that distance. That's our journey distance. Finally, the number of accidents is just that. There's no way to, there's no measurement for that. So the final objective function the authors propose is just this. So you just take the ego agent distance minus the journey distance minus 1,000 times the number of accidents. So this makes this lines up with what we talked about earlier. We want to minimize this value. We want to maximize these two values, and this the smaller this number is, the better our test case scores. And we also have a much higher weight on the number of accidents because this is a considerably smaller value compared to the rest. And we also want more emphasis on the number of accidents because these are, as I believe Xianglin said, relatively rarer in the test training data. So they want to maximize this to see what happens as well. So now here's the final audience question. So we have these two test cases essentially. So here we see what we talked about earlier. So there's a pedestrian, there's a road, there's the initial position of the ego vehicle, and the paths that they'll take, the agent and the ego vehicle will take as well, as marked out by the line and the waypoints. So knowing what we talked about for the objective function, so we just look back again, it's just the ego agent distance minus the journey distance minus 1,000 times the number of accidents. Which test case is the more optimized one, has the lower objective score?
Yeah, so these are very good questions. And the audience would like to have a try. So which scenario, for maybe a more intuitive explanation, that which testing scenarios is more favored to test the autonomous driving system?
Yes, exactly that actually, yeah.
Darren, maybe you can point at students here.
Maybe Alvin, you would like to try?
You asked Yuchen, right?
Yeah.
Okay, Yuchen, are you there?
Oh, it's me. Okay. So I guess it's the one on the right.
Yes, that's correct. So what are your reasons for that? Why do you choose the one on the right?
I think mainly just from eyeballing it, this one on the right looks more dangerous. Actually, the steps, right? It's how do I say, like how do you interpret the step for the pedestrian in this case? Because I guess the distance is like the distance between the ego vehicle and the pedestrian is calculated at each step, right? Then it looks like the pedestrian only has one step.
Yeah, it's not meant to be like a very how to say, a very rigorous representation of the test case scenario, since it's just a simplified version. But so you actually don't really need to worry about the interpretation in a sense. It's just a conceptual overview.
Okay, yeah. So I guess just from eyeballing, this one is more dangerous. It looks like they are going to hit. So number of accidents is definitely positive. Then the path cross, so the distance between them is probably smaller than the other case.
Yeah, exactly those reasons. So here we see this one's the more dangerous one because it has lower total distance, it's an accident, and by a similar journey length. So in terms of the objective score, this one's definitely lower. So yes, exactly just what you mentioned. Thanks. So finally, we've talked about, so just a recap, what we've talked about how the test cases look like. So their representation, which is the noise vector data structure we talked about earlier. We've just finished talking about how the objective function looks like, so how we judged the quality of the test case. And so finally, the last piece you're missing is the algorithm we use to evolve the test cases. So this drives the test cases towards optimization. So what algorithms are applicable? So the authors propose a genetic algorithm, which is quite standard for SBSD, but it's a bit unusual in that they don't use the crossover operator. So the logic that the authors say is that the crossover operator may introduce a reordering of the parameters in noise vector, which may be illegal in generating a test case scenario. So they avoid using the crossover operator for that reason. Instead, they just use a mutation with a high probability mutation. So here, this slide, we just talk about quickly about what a genetic algorithm is. So we just have random population initialized, and each generation, we just generate a new population based on the quote unquote, the so-called best solutions from previous generations. So best here depends on the objective function, which we just talked about. So repeat this process until a user set number of generations has been exhausted, and then we return the best solution. So that's the outcome of the search algorithm. So how is this new population generated? So the authors use a tournament selection. So essentially we select a subset at random and we identify the best member of the subset. And we do this until we get the new population. And then as mentioned before, they've omitted the crossover operator, which is typically what happens in this step. So they will usually, in most usual cases, they will combine genes from the parent cases and get child offspring cases to put in the new population, but this has been omitted for the reasons mentioned before. Instead, they just introduce mutations into population. And they do this using what they call a polynomial bounded mutation operator, which was related to some other paper that they referenced. I'm not quite sure what this exactly is, but they mentioned that apparently using this operator has better results compared to using the standard mutation operators. So now we come to the empirical study. So we've just finished covering the technique, the proposed technique, how it works. So now the authors raised two questions, which is the first has been, does this technique is it actually better? Does it actually generate better test cases? And the second one will be the comparison of technique versus baseline on other miscellaneous criteria, not directly linked to the quality. So when we talk about whether it's a better test case or not, of course, we need to talk about what are the criteria on which we measure the quality of the test case. So the authors have chosen these two criteria, detected failures and failure diversity. I'll explain them more on the next slide here. So the detected failure is just the number of test cases that lead to a collision after the search algorithm. So this is quite straightforward. The more test cases with collisions, the better, because that exposes the failure behavior of the self-driving vehicle. But the next one is a bit more unusual. It's failure diversity. So the idea behind this is that we have test cases, for example, if we have, let's say, 50 test cases, all with detected failures, we don't want them to be the same case, so to speak. We don't want them all to be the same type of failure. We want them to be different types of failure. But it's a bit hard to measure exactly what is a different type of failure. So the authors here use the Euclidean distance between the noise vectors as a measure of the failure diversity. So the idea that hopefully if the two noise vectors are dissimilar, it means that the test cases that they derive from them will also be dissimilar, and it will expose different types of failure in the self-driving car.
By the way, how do they evaluate the difference between the test cases?
Yes, so they just use the Euclidean distance between the failure reviewing noise vectors.
The failure reviewing noise vectors. Can you, maybe I missed this point. How can you raise an example of the failure reviewing noise vectors?
Oh, it's just a test case that's a failure. So a test case that causes a collision, because the test cases are encoded as noise vectors.
Yeah, so can you raise an example? So what the dimension of each vector represents? Maybe I missed this point.
Oh, I didn't. Yeah, I didn't mention specifically what each variable in the noise vector represents, because it's quite long and convoluted. So basically, the idea is that there are different variables in the test scenario, such as the time of day, the color of the car, the positions of the allowed variance in the positions of the agents, and so on. And all of these are encoded as the noise vector.
So in this case, suppose two accidents happens in two different locations. They are supposed to be very different or diversified test cases.
That will be the idea that the authors hope to use, yes, that for two different scenarios, they should be encoded by two very different test cases, which is represented by the noise vectors. And hopefully, the more dissimilar the noise vectors, the more dissimilar the test cases as well.
Yeah, I understand the point, but I'm thinking about its implementation or how to represent, how to do this. So I'm not sure how the encoding, how the noise vectors are encoded. So that's why I raised a question. If two accidents, which is exactly the same type, but they actually happens in very different location. So will their noise vectors very different?
Okay. For that, I'm not sure how to answer you, because I don't have a clear idea of how the test scenario will look like for different test cases as well. I know the parameters, but I'm not sure how the test cases will actually look like, or whether they vary that much, even if
okay, that's okay.
The scenario is the same. Yeah.
Okay.
So with this idea, so now we move on to the PC spec. So this is just some data, what kind of specifications the authors tested their approaches on. So it's just
So they're
standard.
using, so what's the subject of autonomous system is Baidu Apollo.
Yes.
So
So they
Baidu Apollo system has been open sourced, right?
Yeah.
Okay. I see.
Yeah, this is the latest branch, I believe, from what I saw online as well. Yeah. So the experiment setup is that they have a Python scenario runner using the test case generation technique they mentioned before. The Baidu Apollo autonomous driving platform is controlling the ego vehicle. So this is the software that controls the self-driving car, and it connects to the simulator via a customized bridge. And then finally, they have a limit of 200 simulation execution genetic algorithms. So in this case, simulation executions here refers to the product, the generations, and the population size. So it could be any number depending on what the user set population size is. I think they didn't really specify. They mentioned example would be 20 generations times 10 population size, but they don't mention any specifics of which population size they chose exactly for the setup. So here we have the empirical data, and the most important one we see is the number of detected failures. So we see that the new technique generates twice as many failures as random testing, which is good. As for the rest, it's not that large in terms of the difference between the two, but you can still see in general, the new technique produces test cases with a larger average journey distance and a larger average distance on the ego car. But the authors don't put much importance on these two values, just mention them as a side comment, and they mentioned that they might explore the significance of these two values in further research.
Okay.
Yeah. So fine, and next we talk about the failure diversity, which is the second metric we use to measure the test cases. So again, we see that the genetic algorithm performs better in that it produces more diverse test cases as opposed to random testing, which is good as well. So now we come to the challenges. So these are the 4 challenges we've talked about before in general for any paper. The authors only address 2 of them, which is internal and external validity. So whether there are factors influencing results and whether the results are generalizable. So I believe the external validity is what Dr. Lin talked about earlier, touched upon when he asked about whether or not the results for this research, which is only for one specific scenario, can be generalizable to other more general scenarios. The authors will talk about it later on as well. Yeah. So for internal validity, the problem is that Baidu Apollo does not function in a deterministic manner. So the authors have mentioned that many of the failures are not completely reproducible. And additionally, the simulation slow down, the number of test cases go up, which might affect how the test cases are carried out as well. So the authors don't quite address this problem exactly. Just mention these issues, but they don't really address them in my opinion. And next is external validity. So again, it's only a single scenario used. In theory, the approach used, the non-vector approach, should be open for extension. The more complex scenarios provided, they have to extend the number of dimensions or change some of the parameters. But in general, the approach should be generalizable, just that they might have to modify the approach slightly to account for different cases in different scenarios. So that's the defense that the author put up to justify the generalization of the results, in that the generic approach, so converting the test case to a noise vector and running this procedure on it, should in theory be also applied to other scenarios, just that they might have to modify the semantics of the parameters and maybe increase the size of the vector as well, depending. Increase or decrease the size of the vector, depending. Yeah. So the future work authors mentioned they might broaden the scope of research into more scenarios. They might extend the approach with ML-based techniques, and they might explore alternative ML techniques such as use of GANs for discovering more failure-revealing test cases. So that's it for the paper. The takeaways are just we now have software-driven testing in fields that we previously didn't have. So in this case, self-driving cars, we don't expect them now to have digital test cases. We don't have to test them in the field anymore. We can just generate these kind of test cases and run them on the cloud. And it's also a more novel use of SPST in the sense that it's unusual because they don't use the crossover operator, they just use the polynomial bounded mutation operator. Yeah.
I think this is okay. So I think Darren have a very clarified presentations about these SPST applications on self-driving, autonomous driving scenarios. This is a very interesting paper, or more precisely, it is a very interesting topic to pursue. But from my point of view, I just give my comments or my personal feelings. The authors have not fully addressed the problem. And just as Darren mentioned, the generalizability problem is not well addressed, which means that such a testing system is just a semi-automated system. So we still need to manually craft different base scenarios to start the search, right? So I think that is the most this is part worries me a lot. I think in the future there must be some other way for a better presentations for test cases, and the presentation supposed to be but anyway, the presentation could be difficult because when the self-driving car is driving, we need to generate the scenarios some continuously, but might introduce more, but with the potential to introduce more accidents. So yeah, I think there must be the other way. I have a better or a more clever representations so that the whole testing process can be generalized in every or the most scenario instead of we have just one base scenarios and test it. And we're supposed to have the other more generalized scenarios. Okay, so this is basically my comments. Is there any questions for it? Okay, if not, maybe Mengyue, you can briefly share your slides on the topic yesterday.
Okay. Okay. So you mean I just need to introduce this work again, or?
Maybe you can, because some of the students have not joined the meeting yesterday. Maybe you can briefly go through what you introduced yesterday, and then we can have a few questions here.
Okay. So.
By the way, let me ask you, Chen. Oh, sorry, Fan and Chen Zhangshen. Do you have questions yesterday? Hello, Yufan.
Yes, I have some question. Maybe we can go to that page if I remember. I remember
Okay.
I have some.
Okay, so no need to go, no need to jump. Mengyue, you can just go through all the slides.
Okay. So this work named AHNG means representation learning on attributed heterogeneous network is one of my previous work. And in this presentation, I will first give some background knowledge and motivation on heterogeneous network embedding, and then introduce the challenge we may face. And then is my framework. So let's start with the motivation. So first, we would like to say what is a network embedding. So, the goal of network embedding is to automatically learn a transformation from the original input data to new latent representations, so that the new latent representation can be effectively applied to various downstream tasks such as anomaly detection, clustering, classification, and link prediction, thereby liberating people from tedious feature engineering. It can be seen that the input network can be in various forms, such as homogeneous network, heterogeneous network, or graph with auxiliary information, such as node labels. As for the output, the granularity of embedding can be determined according to the specific task, embedding of nodes or edges, or the whole graph, and so on. And in this work, I focus on embed an attributed heterogeneous work and embed the nodes and give the node embedding. So first, we need to distinguish the difference between a heterogeneous network and a homogeneous network. A heterogeneous network has multiple types of nodes and edges, but a homogeneous network just have one type of nodes and edges. And as shown in the figure, the left part is a simple attributed heterogeneous academic network, including 3 types of nodes authors, papers, and venues. And each node has its own attributes, which are represented by different colors. And the red part contains two homogeneous networks, which are respectively mapped from the left part. The upper is a homogeneous network mapped based on the collaborative relationship between the authors, and the network below is mapped based on the author's research fields. That means generally the network we study is a homogeneous network, which is mapping from the attributed heterogeneous network.
Sorry, I have a question here. So
okay.
Yeah, so when you use the attributed this network, heterogeneous network, so if there are this picture, you have three nodes. There's other venue. Yeah. So for the every node's feature, so if the other attribute, so it only has the feature of the other. You mean here is F1 and F2. So 0 for the F3 to F6. Is it true?
Yeah, that's true. That's right. So, that's way I construct my attribute matrix. You can, that's a way to construct the matrix, but you can use other way to construct it.
Yeah. So originally you just gave the node of the people with only F1 and F2. So after your message passing or like model training, then this node, this other node will also have F3 to F6.
Yes. Sorry, could you just see again?
You want to find to repeat, right? So you can also reorganize your sentence to make yourself more expressive and clarify. Have a try.
So for example, for this node, originally it only have two features, is F1 and F2.
Yeah.
So after the model training or message passing, then the other node like F3, F4, and F5, F6 will pass to this node, and then this will not be 0.
Yes, yes. Actually, after the embedding, all the types of nodes are mapped into the same latent space. And that means in that space, their features, their representations will be in a lower dimensional space, and the embeddings will not be separated like this F1, F2. They just continue. They just be represented such as a continuous vector.
Continuous vector.
Yeah. Yes.
Maybe I can.
There's vector. Yeah. Yes.
Maybe I can rephrase it. Mengyue can correct me if I'm wrong. So I think Yufan first point out that, for example, given a person, it has a feature like gender, right? And given another object like paper or venue, it will not have such a feature, but it will have the feature like maybe the city or whatever it is. So Yufan's point, Yufan can correct me if I understand it not good enough. So in this case, if the message passing or through the message passing and the training, where different features will be entangled all together. So maybe that's Yufan's question, if I understand it correctly. And I think Mengyue addressed these questions by saying that indeed the feature may be different, but the point is that all the nodes will share embedding space right? A dense embedding space. Maybe the feature, maybe each feature is a discrete value, like man or woman, or like the city, whatever it is. But after they project into the same space, and all the nodes will share the same space. So in this case, these features may be entangled together, but anyway, there is a universal representation for all the nodes. Right. So that is basically what I understand. Yeah.
So follow my question is that, so what's the difference between heterogeneous? Because if you finished passage passing, all the nodes are in the homogeneous. Could you understand my idea? Because after you message passing, that it's not heterogeneous, homogeneous, because all the nodes have 6 features. The only difference is that originally you just assign, typical some different features to different nodes.
Yeah, actually, I think node embedding technique is just upstream task, and it's not a homogeneous network. If we map them into the latent space, they are also heterogeneous. Yeah, we can't treat it heterogeneous, although they may be represented in the same space.
Maybe I can rephrase it. I think the question.
Am I right?
I think this is a very good targeted and the attack and defense. So I think in the teacher defense, I think some reviewers may also raise the similar question like define. So what is the borderline between the heterogeneous and the homogeneous, right? So I think one of the way to address it is that yes, indeed, when the nodes are sharing the same universal space, it looks like a homogeneous. But one way to address the heterogeneous problem is that to convert them into a homogeneous system. In this case, it allows us to using some existing technique. I'm not sure whether that is true because I'm not an expert in graph neural network model, but basically that is how we address the question. Mengyue, am I follow the point?
I think you're right. Yeah.
Okay, Yifan, do you have any other questions here?
No, actually, thank you.
Okay, let's keep going on.
So, let's see the challenge when we want to do heterogeneous network embedding. The first challenge is how to fuse heterogeneous information sources. As we can see, there are 3 information sources: network structure information, and the semantic information, and the diverse nodes attributes. So how to fuse them, right?
Sorry, you raised a question or?
No, I just, yeah. So the second, why? Okay. The second challenge is how to capture the uncertainty of node embedding. I will use 2 examples to explain it. As shown in the 2 figures, the left one is a heterogeneous movie network, where the blue node represents a director, the yellow node represents a movie, and the green is its movie type. The blue node here represents director Christopher Nolan. We select 4 well-known movies from his work, namely Memento, The Dark Knight, Inception, and Dunkirk. Among them, the Memento and Inception are suspense films. The Dark Knight is a science fiction film, and Dunkirk is a war film. When we want to embed the node of director Nolan, how should we weigh the influence of various movies on this node embedding? And And this phenomenon also exists in the semantic network because words have different semantics in different contexts, right? So I abstract such phenomenon into the picture below here. The right node in the center connects 3 different types of nodes. When the attributes of this node are different or even opposite, how should we embed the right node in the middle? Most of the previous network embedding methods embed nodes into a vector, depicting a node as a single point in the latent space, leading to a certain representation of a node. Intuitively, attributed heterogeneous network embedding model should learn the representation of a node based on its neighbors, related links, and node attributes. Hence, the embedding of each node should have a floating range to show their uncertainty. Therefore, in response to the above 2 challenges existing in the attributed heterogeneous network, I propose a model AHNG. The problem definition of AHNG is giving an attributed heterogeneous network G, where V is the set of nodes, E is a set of edges, and F is a set of node attributes. We aim to node belong to V with a Gaussian distribution in the lower dimensional space. And the framework of AHNG is shown in the figure. It consists of 3 essential components: attribute encoder, metabase-based random walker, and the learner. And the AHNG
Mengyue, so I have questions. Why it has to be a low dimensional Gaussian distribution? So if I understand it correctly, so each mu is a lower dimensional vectors, or
and the Gaussian distribution has 2 parameters. One is mu and the second is sigma.
I got it.
So the mu we can treat the mu like this certain location, right? And the sigma shows its floating how to say?
So maybe Ruofan can complement it here. So Mengyue, can you go to the slide?
This?
This framework slide. So
okay.
So if I understand correctly, each node, anyway, so each node will have an initial feature, right? And it will be projected into a lower dimensional space. And each dimension of the vector will have to conform to a Gaussian distribution. I haven't picked up a very.
So it's like instead of using a fixed encoder, we use a variational encoder. So instead of predicting it as a fixed embedding, we predict the distribution.
To improve the randomness of the model.
So sorry, I
lost uncertainty.
Sorry.
I think the rule of thumb, I think the rule of thumb means that it's more like the idea of the variational autoencoder. I'm not sure you are familiar with VAE.
I know.
Yeah, you know, right? So the VAE actually is not to learn a fixed embedding. It's basically to learn a distribution, and based on the distribution, the decoder of the VAE can generate a lot of diversified picture. So this is so the question here is whether so the mu and the sigma is what you want to learn, right? It's a parameter, especially parameter. So in this case, you are learning, you borrow some idea which is similar to VAE. And Oh no,
Actually, they are
nothing's
not.
no.
Yeah,
They are
they
not
are
the same.
different. You know, VAE, in VAE, we will use Gaussian distribution to capture all the node distribution. We dissect the node distribution, right?
What node distribution?
The node, all of the node distribution.
Yeah,
Yeah.
VAE.
We would like to capture the whole distribution. But in this scenario, we just represent each node as a Gaussian distribution. Yeah.
But okay, so I got it. So for each node, we have a Gaussian distribution in a lower dimensional space. So, but during the execution, it means that the node will have a set of variant vector, right? Because what we learn is actually a distribution. So when we run the model, each node will have where it will have a non-deterministic vector there.
Non what?
Non-deterministic means random.
Okay. Yes.
Yeah. So that means each node will have a random vector conforming to lambda distribution.
Yes.
Actually, I think in the AE, we will input some node features, right? And in our model, we also input the attribute matrix.
Yes.
So the initial vector of each node is not randomly generated.
Yes, you're right.
It's their attribute.
Yeah, I understand. The attributed feature is fixed.
Yeah.
But after the embedding, but anyway, what you learn is actually a distribution instead of a fixed embedding. So it means that once you give it an attributed feature, it will convert it into a Gaussian distribution. And based on the Gaussian distribution, we will randomly sample an embedding from the distribution. So that
I know. I know. Yeah. Actually, in my experiment, I use mu to do the following task. And yeah, yes.
That is still a fixed embedding.
So maybe I can simplify the question here. So since you are learning a distribution, right? So do you need to sample an instance or a sample instance from the distribution, or you're just using the distribution to do the prediction? So or how maybe I can put this: does the node embedding or the lambda node representation fixed or not? Fixed means that
fixed. Yes.
Fixed. So each time. So that means each time. So given a attributed feature, and after conversion or after the transformation, its node embedding will be always fixed. Or the node representation. So let me put it this. Maybe so here is the feature embedding, the feature vector here. So this is the feature in vectors. So whatever it is, we have a black box. It could be could be a neural network model, or could be a graph neural network model, and we will have a representation vector R, right? So so here, if I understand it correctly, this R is Z, and each Zi will follow a distribution, right?
Yes.
All right. So in this case, what we have is a distribution of the embeddings instead of an embedding per se. So in this case, if we really want to use the system, so giving a feature vector, and we will have a distribution, but this is just a distribution after all. So the next to do is that maybe based on mu or sigma, we need to sample a real, a concrete or an instance embedding here. I use it R prime. So by right, we suppose use this vector instead of the random distribution.
Actually, you can use the just use a mu, just use a
Oh, I got it. You
mu
do not,
in the distribution.
So you assume that the variance is 0.
Yes. The mu represents that the node will be the node have the higher possibility to be represented as mu. The mu the vector represented by mu. Yeah, but the sigma is just it has some.
But the point, my follow-up question is that will the sigma use for in the application?
You mean what does sigma?
Yeah. So you understand. You learn the mu and you learn the sigma, right?
Yeah.
And you only when you are running the models, you're only using mu, which means the sigma is therefore at 0. Right?
No. When I optimizing my model, the mu and the sigma are simultaneously optimized. Yes, but if you want to do the following task, it's difficult, maybe uneasy to use them both to do the following task, right? So, but the mu can highest possibility that the node will be represented as one. Yes,
I got it. The mu and the sigma are parameters learned through the training. If so, I just think about it. When we run a model, if we do not use the sigma, it means that it will lose the feature or lose a bit. It may not maximize or utilize this power of distribution. It is just a common sense. For example, in EAE, right? So we're using mu and sigma. We have mu and sigma. So mu and sigma, anyway, mu is fixed, and the sigma allows us to generate a diversified sample. For example, if we want to synthesize the human face, the mu is just be there, and the sigma allows us to have a face with variant eye, ear, hair, etc. But in your case, you do not require such a randomness, right?
Yes. This is a graph, and you see is in some vision problem, right? So they are different, I think.
I understand the different, but when I understand you learn sigma, here, but this sigma will not be used when you are running a model. Am I right?
No, I use sigma.
But you use sigma, but if I remember correctly, you are saying that you only use mu to pass to the prediction, and the sigma is not used.
Maybe I said it means that mu and sigma are both trained during.
Yes, I understand. You mentioned that mu and sigma are trained simultaneously. But suppose we have trained the model.
Yeah, but in other following tasks, not my other following tasks, it's not easy to use mu and sigma simultaneously to run, right?
So maybe can I summarize on this picture, on this slides here? So we do have the distribution. We do learn the Gaussian distribution, but once the model is when model is training, and we will train both mu and sigma, and the weights of them will be updated. Once the model is trained, we only use mu to get the model or to get the node representation.
Actually, you can use mu and sigma together. It depends on your own task. If you can use them both, you can just use them. But when I test the efficiency of my work, I just use mu.
And also, the follow-up question is that, do we need a randomness, right? Do we need the randomness introduced by the variance? It also depends on, maybe if you use one of my follow-up questions, supposed to be why we need to introduce the randomness. Because once you have a sigma, if you want to use sigma, it means that each time we run a model, we may have different results. Right, because the embedding will be different.
Yes.
And under what scenarios do we need such a randomness, or under what scenarios do we do not need such a randomness feature? So that is also but anyway, so it's good. But anyway, it's good to know that when we train models, you basically learn the distribution instead of fixed embeddings.
Okay.
Okay, maybe we can maybe we have enough discussions here, and also we need to leave some time for Xianglin to give this QE rehearsal. Let's keep going on.
Okay. So that's the attribute encoder, and it's a simple, yes, and should I introduce more? Explain more?
Yeah, so maybe I have a more question about uncertainty. Can you re-emphasize why the uncertainty is the second challenge, or is a challenge?
We can use this example, and we can see that Memento and Inception are suspense movies, right? And the Dunkirk is a war, right? So these movies have different thematic meaning, right?
Yeah.
But when we embed Nolan, this node, we would like to know which of them should be more contributed to Nolan's embedding. Right? They are different, but
in this case, we just need to propagate the features into Nolan, the actor of Nolan, right? And
yes.
I agree with you that the features or the recommendations on each node is based on its context or based on its neighbors. But in this case, how this can relate to the uncertainty? As long as we equip this node with different neighbors, we will just address your seemingly the challenge, right? So, for example, giving the node Nolan or giving the node a science fiction, sorry, so giving the node maybe the Dark Knight, right? Suppose we add another link. We add another link. Maybe we call this maybe romantic, or maybe that is another topics of the movie, and its embedding will just be different. How these will be related to uncertainty, and basically it seems to be certain to me as long as we equip a node with a different neighbor, and its embedding will just change accordingly. And how it could be uncertain?
It means that this is a certain embedding, right? Just a vector. And this this is the this is an uncertainty representation. It means the node can be embedding here, 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 or here. It's all right.
What's the benefits if we fix?
I think here the example is if you want to describe the profile of this director Nolan, if we only use one single number to represent the genre of movie he directs, then maybe we see that there are two movies belongs to suspense. Then one may assign Nolan as suspense, but actually he has directed many other kinds of movie. So instead of having a fixed label, we might want to have some distribution. For example, this bar represents suspense, and this is science fiction, and this is war. So in this way, it has a distribution. But this one is a discrete case, so you will have a discrete distribution. But once you want to represent it into a dense embedding, then you will have a continuous distribution.
Yes.
Yeah,
Right.
I got a point. But even a fixed vector isn't a fixed vector expressive enough to represent such uncertainty. So for example, we just learned softmax. A softmax, we have 3 dimensions, each dimension corresponding to one genre. And that encoding is also enough to express such an idea.
Yes, but softmax can also be seen as a distribution.
Yeah, I understand the idea of distribution, and I think Ro can make a very clarified complement about to interpret the idea. So here what I linger on here or stick on here is that my question is more revolve around the necessity of using distribution to learn a Gaussian distribution instead of learn a fixed embedding. So here, but anyway, so I just raised the question here. Maybe Mengyue have more expertise to address this. So my question to Mengyue here, or my comments to Mengyue here is that maybe because I'm not quite sure whether the learning a distribution. Of course, I understand learning distribution is good, but it seems to me that since when you are using the model, you do not using the theorems. And your idea or your rationale of addressing uncertainty can also be addressed by, it seems to me, can also be addressed by a fixed vector instead of the irrational vector. Okay, maybe that's enough discussion. Maybe we can have more offline discussions, but maybe we can keep going on for the next slide.
Okay.
Yeah, we may need to leave some time for Xianglin to give the QE. Yeah.
Okay. So that's a MetaPath based random walker, and this will capture node structure and semantic information. And the objective function is just simple. It's a negative sampling. It uses negative sampling strategy. And we use KR divergency to measure the dissimilarity between two distribution, to know the distribution. And that's all. Yes.
And by the way, so can I ask how do you aggregate the nodes? And how do you aggregate the nodes? So there's neighbors, right? So
yes.
given a node, it has a few neighbors. And what aggregation operators did it apply?
Could you please say it?
Speak it again, or
yeah.
my point is that given
repeat
a node,
it. Yeah.
Given a node, right? It has its neighbors, right?
Yes.
And
yes.
The embedding of the neighbors actually will have an impact on the target node, right?
Yeah.
And how do you aggregate such a impact, or how do the neighbors exert its influence on the target node?
Oh, I see. Actually, we treat them as same weight.
Same way, you add them together or take an average.
What?
You add them
Sorry.
together. So suppose we have this target node, we call it node NT, right? And
You
there
can-
is neighbor N1, N2, whatever it is. So they will have their
Yeah.
embeddings, and how they propagate their information to
Oh.
NT.
Let's see the objective function here. When the center node is VI, right? So the VI is ZI. The node embedding of VI is ZI. And the next per neighbor may be P4, right? And so the VG may be the P4 embedding. And then we will select a negative example, which have the same type with ZG, but are not linked or show in the neighborhoods. For example, suppose it may be.
I understand. So there's a negative sampling. I understand the negative
Yeah.
sampling. Okay. So it means that the aggregation, the functional aggregation, is a length or trend.
Yes.
So giving two types of nodes, if they are in the same window or if they're neighbors, and their relation is actually a trend, right? So this edge means a network. Am I right? Or is there something else? Or is scalar divergence?
Yes. Yes, it's clear divergence.
Okay, I got it. So basically you want all the nodes in the same windows as similar as possible, right?
Yes.
And in this case, if V1 and P4 are exactly the same, have exactly the same distribution, and the object function will be minimized, right?
Yes.
Hey, Yufan, is it Yufan there? Hello, Yufan.
Yes, yes.
What's your opinion here?
I didn't quite get it. Could you explain?
Okay, the point, maybe Changshen can also join the discussion, or maybe Dr. Xiaoyan can also join the discussion. So maybe I'll repeat it here. So in Mengyue's approach, here this is a sliding window. Given a sliding window and all the nodes are considered neighbors. And here the objective function is that because each node is actually a distribution, is encoded into distribution. So this scalar divergence is basically a similarity function to make sure all the nodes within a window should be as similar as possible. And in this case, there's no aggregation. There's no node aggregation. So the overall function is just to minimize the distance between the neighbors, if I understand it correctly.
Yes.
Right?
I think.
Yeah,
I think you're right.
yeah. You found. What's your point, or Changchun, do you have an opinion here?
I didn't have any opinion. I didn't use this before. Maybe I can.
Yeah, maybe you can investigate it. So my comments here is that this heterogeneous network can be our graph network. For example, the method correlations, the correlation between method and method, the definition relation between variables and class, and the correlation or the declaration relation between class and method can also be considered as a heterogeneous network, right? So maybe we can, there's something we can borrow here. but I have it worries me a little because the aggregation functions not that obvious to me, and yeah, and the neighbors, it seems to me, have too much influence to the target. I just have such a concern, but I may not write because I myself may not try to hear, but I just have a concern that the relations or the influence of the neighbor seems too strong. And after all, you're using a KR divergence. So suppose two neighbors share exactly the same distribution, including the mu and the NUS, and it will just minimize the function, minimize objective function. So that is my concern here. Okay, maybe if there's no questions, let's
I
keep.
have some more questions. So why do you need a sigmoid and a log function outside the KL divergence? Hello,
You mean why?
Yeah.
Hello.
So,
you mean
so
why we
sigmoid.
don't use the sigmoid function, right?
Why we use, because can we just optimize the KL divergence directly?
Yes, yes. Here it's use this. Sorry.
I think the question is simple. So why do we need to add a single mode function, apply single mode function after we already have clear divergence?
Because you want to measure the two distributions, not the two vector similarity.
I mean, can you remove this part? Can you remove this?
Remove this? No. Actually, this is a no. You cannot remove this. This actually, this function is our objective function. This function is the real function, but it's not. It's not easy to compute this. It's very computation expensive. So we use negative sampling to simplify it.
Oh, so the log actually comes from here.
Yeah.
And the sigmoid is because you want to model the probability, so you need to normalize it.
Yes. So we cannot remove them. Yeah.
Okay. Yeah, I get it. And also, how many parameters are inside this sigma? Because sigma is a matrix. Then if you have a separate sigma for every node, you will have many parameters to optimize, right?
Yes, that's right.
So did you make any simplified assumption on sigma?
Sigma is a matrix, right?
Yeah.
It means it may have k times k parameters, right?
Yeah.
But we have a simplification, such as we just suppose the sigma. Yeah.
Okay. I think I get it. So yeah. Thank you.
You're welcome.
Okay, so that is very interesting discussion. So let's move on. So now we can go to the experiment part, right?
Yes.
Okay, so we can briefly go through the experiment. Yeah, I suggest you can also raise some questions here.
The experiment is just simple, and we use a minor an academic network. And here are some parameters of the baselines. And these are results.
Okay, so maybe you can skip the results there. Since it's already 4 p.m. So I think it's a very interesting talk. Yeah, but as a paper, what is missing is that what is the most competitive baseline when this paper is published? So this is some part missing, and also
Yeah,
okay, so
this one. Okay, you make the meta path to vector. Actually, you can see it may set the walk length as 100 and how to say the length is 100 1000 and he walks on each node 100 times. But in our model, we just need to say sorry. Oh, sorry, I didn't show it, but we just need to maybe 10 lengths and 5 walks. We can get a good result.
Okay, that is impressive.
Yeah.
Okay, so maybe a final comment here is that anyway, it's a very good, very interesting talk here, and we have a very hot discussion. And one thing I still didn't follow or still have some question is that whether the distributions, whether we can, is it possible that we just using a fixed embedding instead of distribution, encoding distribution? And that may also makes all this function simplified, right? So we do not need to use the Kerr divergence. We can just
yeah, I think you can just use a vector to
learn in this case, right?
Mu layer or the sigma layer. Yeah, you just can single layer. Right?
Yeah, thanks, thanks Mengyue. Yeah, so I think your voice is a little disrupted, but that's okay. Anyway, thanks for your sharing. That is really a very interesting topic. If any student is still interested in this work, I suggest you contact Mengyue offline.
Thank you.
Okay, so Xianglin, are you ready?
Oh yeah.
Okay, so now it's time for Xianglin's rehearsal.
Yeah.
Yeah, so Xianglin is now going to an important milestone in your PhD.
Sorry.
In your PhD, yeah. So let's have a rehearsal. The time supposed to be half an hour, right?
Yeah, half an hour. But I haven't really measured the length of my presentation myself. I'm not sure. Maybe today we'll see how long it takes.
Yeah. So if you think if we are not that ready today, maybe we can also have a rehearsals in next Wednesday. So let's keep going. Yeah.
Yeah. So I just start.
Assuming that all the audience are professors in the community.
Yeah, so hello professors. My name is Xianglin. I'm supervised by Prof. Dong, and my QE topic is towards a record and replay visual debugging system for deep classifiers. So today my presentation will be covering 4 main parts. I will start from background and related work. To show you that the direction is a visual system, and then followed by our first attempt towards visual system, which is DVI. So I will talk about the preliminaries of DVI and then technical solution, finally some experiment results. On the third part, I will also introduce some case studies where we apply DVI on. So we have 2 case studies here, active learning and noisy data sets. Lastly, I will talk about the future direction. And so we know that deep models are everywhere now. Deep model has achieved state-of-the-art performance in many research areas like machine translation, automatic driving, some object recognition, and voice recognition. So it seems inevitable that those high-performing complex black box models will become increasingly prevalent and important in the future. But note that deep model is programmed as well. And if it's a program, it can have some bugs. The model, however, the model debugging, which means the diagnosing and fixing model errors process, still remains a long-standing challenge. Here I list out some model defects or errors. So different from some traditional bugs, which could probably cause system crash, so that you would know there's some bugs. The model defects can sometimes be silent, but still bring undesirable results. The first observation by us is that the adversarial training can hurt generalization. We know that deep models are extremely vulnerable against some adversarial attack. That means if you perturb the input a little bit, then the model could probably give some wrong prediction. So some researchers propose to do adversarial training, which just use the adversarial sample to retrain the models in order to increase robustness. But the observation here is that although the robustness accuracy did increase when you do adversarial training, on the right column. However, at the meantime, test accuracy, the standard test accuracy would decrease, but still we don't know what caused this phenomenon. And the second observation is that mislabeled data widely exists in many data sets. The data is very important for machine learning tasks, but now some research even found that there are mislabeled data in some well-known data sets like CIVA10. But because data is manually labeled and humans could make mistakes, so it's a problem. We still don't know what would happen if you train your model over some mislabeled data. Apart from those two observations, the source of bugs can come from many different components like training data itself or model structure. For example, if you use a rather simple model structure for a complex task, then it could have some problems. And developers could probably have some errors inside their code. And if your model is initialized with some bad hyperparameters, then the result might not be good. So overall, if you observe some poor performance and low accuracy on your model, can you tell what's the root causes? So yeah, the question here is how can we track the observation back to root cause here? Some state-of-the-art method is visual explanation method. So visual explanation method, its primary goal is to providing insight to end users, but still some researchers use them to be a debugging tool for models recently. One very popular method is individual-based explanation. Existing work including GradCam, GradCam++, or integrate gradient. But the overall idea of those approaches is that by perturbing the inputs or calculate the gradient of inputs, they wanted to find the most important pixels or important features in the input that makes the model to have such prediction. Yeah, on the right is an example of GradCam. So on the first row, the model predicts the image to be a cat, and this method managed to highlight the pixel of cat bodies. And on the second row, the model predicts the image to be a dog, and yeah, still this GradCam managed to highlight the pixel on dog face. Although this method could serve as potential debugging tool for for finding the superior correlation. For example, if the model predicts the image to be a dog, however, the method highlights pixels instead on dog itself, but on the background, for example, then it could be a superior correlation. But but this explanation method cannot give us insight or give us explanation on the problem that we talked about in the previous slides. One probably most related work is called Deep View. So Deep View wanted to visualize some training points along with the boundaries for image classifier. But the shortcoming of it is it's very inefficient and it can only work on probably 200 to 300 data points. So it's not scalable. The biggest limitation is that it's a static method, that it can only show the visualization of one well-trained model. It cannot track the change in the training process, which cannot give us insight on how the results are formed. So that gives us the motivation of our research work. We argue that it's very important when we try to diagnose a model defects, we need to track the root cause to explain the model's behavior. And we need to highlight how the progressive information is formed during the training process. So in contrast to Deep View, we wanted to visualize the training points along with the classification landscape in the whole training process. Another rationale for our work is a strategy called record and replay in software engineering research area. This strategy wanted to record every step of the program's process and thread execution and deterministic and non-deterministic inputs. So they record everything and store it into a disk in a log. The recording later can allow the user or developers to replay it and debug exactly as it happens, as the bug happens. So inspired by this, we ask what if we can have a visual system for human to see the training process? So can we have a debugging system for deep models as well? But then another problem is that what should be checked when recording the training process? Someone may say checking some individual variables like loss or accuracy, but that gives us little insight. Like I talked about before, if you observe that loss is not decreasing or your accuracy plateaus at some points, still you cannot know what the root causes is. And another possible solution is to check some individual samples representation along the training process, but that still cannot provide so much information because there could be some outliers and it cannot explain the overall model behavior. So that's why we argue that a summarization of training points and classification landscape are more important than visualizing some individual samples. So in all, our solution here is to have a visualization of training points feature vector and the corresponding decision boundary, which is the classification landscape itself. And then the visualization problem naturally becomes a dimension reduction problem. The first challenge is that there must be some information loss during the dimension reduction. But what information should we preserve is a problem. And the second is the efficiency and scalability. For example, the deep view is not efficient and not scalable. So here the question is how to make the time overhead and space overhead acceptable for our own work. The third one is the temporal continuity. Some existing work rely on some random initialization, which makes their visualization not stable. The visualization results given by same data could be different. But if we wanted to see some training behavior along the time, we must stabilize the visualization. Next, I will first show an example of our work to show why this visualization can really help to find the root causes to some model defect. On the previous slides, we talked about a problem. Why is adversarial training sometimes cause the degeneration model? So here the visualization is given by one snapshot of the model. So first I would introduce what it means of the background and the points. So each point represents a sample and each color represents a class. The color of points represents the label of samples, and the color of a region represents a predicted class. So here, for example, if you see a red point lying on blue territory, then that means it is labeled as the class of red and then predicted as the class of blue. Moreover, the color shade indicates the confidence of a prediction, and confidence area are generally lighter. The color would be generally lighter. And then here, the model fitting process is visualized by the process of classification boundary being reshaped, and those data points were being pulled towards the territory of the corresponding colors. And here we can show, by using this tool, we can show that decision boundary reshaping, this boundary reshaping process is happening when the model is adapting new adversarial sample and training samples. And then there's a trade-off being made when adversarial sample robustness increase and testing accuracy decrease. And here, for simplicity, we only show one testing sample with its 10 nearest adversarial samples in case you are overwhelmed by other training samples. So here, the red points with yellow circles is the testing points, which is correctly classified at first because it lies on the red territory, and around it is its 10 nearest adversarial samples. At first, the adversarial samples are wrongly classified. And then in the next step, the adversarial samples are being pulled to their correct territory in the adversarial training process. And in the meantime, the test samples are being pulled by its surrounding points. And then later, this process ended with the testing sample being wrongly classified, and all the adversarial samples are correctly classified. So this tells us why the adversarial training could sometimes cause the degeneration of a model. That means some of our testing samples, which could probably look like some adversarial samples, and then in the training process, it is being pulled by its surrounding adversarial samples. And here we show the animation of the overall adversarial samples and test samples. On the left is the adversarial sample animation. So at first, sorry about this, maybe next time I will fix this problem, but on the right is the adversarial sample animation. So at first, the adversarial samples are wrongly classified. And then through the training process, they are pulled into the correct region. And on the right is the test sample. They are correctly classified at first, and then later going to the wrong territory. And we also design a visual system framework to support this tool. And so first, the user should input some subject model, which is the snapshot of the model in the training process. And next, we would have a visualization model trainer to deal with the subject model. And then in the third step, after we got the visualization model, user can have some queries in the front end. So that's the fourth step. After they send some queries, it can be passed by the query parser and deal with. And later in the next step, the result will be sent to the front end and user can look at them. And then this is an image of our front end, which can which have some search box, and on the left, by press the previous and next button, it can go through time to see the visualization of different epoch. And on the bottom left, we also have some metrics to evaluate it, how good the visualization is. But overall, we wanted to say that this system has an open-ended exploration features that can check the dynamics of evolving classification landscape and corresponding training embedding. And it can also support some interactive front-end interaction with users. Next, I will show the technical solution to our tool. So one of the challenges we mentioned is that there's definitely some information loss when we do dimension reduction. But which information is the most important that we should preserve? So here we propose 4 properties that the visualization should satisfy in the dimension reduction process, which can be helpful for the causal analysis. The first one is neighbor preserving property. The second is boundary distance preserving property. The third one is inverse projection preserving property, and the fourth one is temporal preserving property. Next, I would introduce them one by one. The neighbor preserving property is natural needed for dimension reduction. Just like in our example of adversarial training before, we see that looking at neighbors is very helpful for analyze the behavior of model training. And how do we evaluate it? This is that for any training point xi, and we want to find its k nearest neighbors denoted as nkxi, and for the counterpart of xi, in low dimensional space denoted as yi. Again, we find its k-nearest neighbor points denoted as nk yi, and we calculate the intersection between those two sets, then normalize the result by k. Finally, we sum over all the results and average out. So that's that's neighbor preserving property. The second property is boundary distance preserving property. We know that boundaries are very important features of deep models. Actually, there are more and more research work that aims to analyze the decision boundary of deep models. To understand the boundaries can help to evaluate the model robustness and model vulnerabilities. Another motivating example is active learning. So active learning is an learning activity that's opposed to passively taking in all the information. Instead, it tries to actively select some informative points from unlabeled data pool. So, and then query for the label of informative points. So this happens when querying for the label is very expensive. And one well-known approach is called uncertainty approach. So it defines and measures the quality of uncertainty to select uncertain data points, which means it tries to select data points that lying on decision boundary. But you could probably ask, are the samples selected by some strategy or lying on decision boundaries or not? Or are they at the least close to decision boundaries? How do you verify this? So since this is very important, we need to preserve the boundary information after dimension reduction. How to calculate the boundary distance preserving property is that for any points xi from training data set, we can find, so here we assume we have a set of boundary points that can well represent boundary itself. And for any training point xi, we find its k-nearest boundary points denoted as nkbxi. And for the counterparts of xi, yi, we again find its k-nearest boundary points in low dimensional space, denoted as nkb prime yi. So next, we calculate the intersection between the two sets and then normalize the value by k. Finally, we sum over the value and average out. So that serves as the value for boundary preserving, distance preserving property. For the third property, this is called inverse projection preserving property. On the middle, we show a example to project some original input to low dimensional space, which is the compressed representation. And then by using an inverse function to reconstruct the original input. To use an inverse function to reconstruct a similar input can guide the compressed information to contain more important information that can help to reconstruct the original image. So so here we can apply the MSE, the mean square error function, to define the inverse projection preserving value. So we calculate the distance between the original input and reconstructed input and average out the value for each sample that can serve as inverse projection preserving property. The fourth property is called temporal preserving property. So remember that there's some existing work all rely on random initialization. Here I show 2 runs of visualization result of minced dataset given by one state-of-the-art baseline UMAP. And even though the input data is the same, the visualization result is different. On the middle, the position of 3 cluster changed. But since we need to align the visualization result over time, this cannot happen, so we must have continuity over time. And the intuition here is that if a sample with same semantic or similar semantic between 2 epochs, then their low dimensional position should be the same or at least close. So how do we evaluate the semantic of an sample? Is that we take the representation of some sample xi from time step t, and then we take the representation from time step t plus 1, and then we find the k-nearest neighbor at time step t and find the k-nearest neighbor of xi at time step t plus 1 and calculate the intersection between 2 sets. The rationale here is that if the neighbors of some sample did not change over time, then its semantic should still remain the same or similar. And then later, to evaluate the temporal preserving property, we just calculate the Pearson correlation between the semantic of some sample and the low dimensional position change. So that's the temporal preserving property. Our approach here is to, the high level idea is to construct an autoencoder to do the dimensional reduction and inverse projection that can satisfy the 4 properties we mentioned before. And then the visualization solution should contain 2 parts. The first part is a projection function that can project any feature vector from edge dimension into low dimensional space with dimension L. Because we are trying to visualize the results, so the L should be 2 or 3, so human can understand. And then the inverse projection function should have the ability to map any points from L dimension back into H dimensional space. The overall of our research work is that first, we save some subject model from different time steps as recording. And then for each subject model, we train a visualization model or autoencoder that satisfy the 4 properties, and then use that to visualize, and then use that to generate some visualized result. And because we need to have this temporal preserving property, so each visualization model will be initialized by the visualization model in a previous epoch. And then in order to introduce how we can satisfy the neighbor preserving property, we need to first introduce some preliminaries on dimension reduction. There's a broad research work on dimensional reduction. mainly it can be split into two parts. The first part is some linear method like PCI and kernel PCI, which tries to find the principal component and then only reserve the top, probably top 2 or top 3 direction. And for the nonlinear method, we have some works like TSNE and UMAP. The high level idea is that they wanted to preserve the neighbor after dimensional reduction. The most important or related work to us is UMAP. So UMAP is, the full name of UMAP is Uniform Manifold Approximation and Projection. It's a dimension reduction technique that first it tries to model the manifold with a fuzzy topological structure in high dimensional space. And then in low dimensional space, it will search for a closest possible equivalent fuzzy topological structure. That way, we can preserve the neighbors after dimension reduction. So what it do is that first, it calculates the similarity between any 2 points, let's say I and J, by using this radius kernel. And then for symmetry, it will normalize Pij to be the second formula. And then in low dimensional space, you will use a student T distribution to measure the similarity between any 2 points I and J. And finally, they will use this KL divergence to match Pij and Qij. The first part, the rationale of first part is that they try to make similar points as close as possible. And for the second part, they wanted to make sure any points that are far away should still be far away in low dimensional space. So for the neighbor preserving property, we wanted to mimic the process of UMAP. What UMAP do is within the graph A and graph B. So first you have some training points, then you compute this fuzzy topological structure, which is you need to link each point to its k-nearest neighbors, and then construct a graph. And later, by learning embedding that can preserve the structure of this graph, so they can project the structure from 3D to 2D. And in our approach, we have an encoder and decoder to do that part. So first we will construct the graph accordingly and get the similarity between any 2 points I and J, and later to use their cost function as our loss function to preserve the structure. That's how we achieve neighbor preserving property. And then for the boundary distance preserving property, the first step is to estimate the boundary. And in our paper, we first give a formal definition of a delta boundary. We wanted to find boundaries. We defined that if a boundary that can satisfy the prediction of its top 1 class and top 2 class, the score for top 1 and top 2 class to be less than some predefined value, delta, then we say this point lies on decision boundary. And then the next step is to generate some boundary points. One very intuitive way is to conduct a adversarial attack to generate those points that satisfy our definition. However, there is problem of efficiency, because to calculate the gradient in order to launch an adversarial attack is computationally expensive. Instead, here we apply a mix-up method, which makes two images, and that could be very efficient in our setting. And then there's a trade-off between efficiency and diversity. So we would also want the boundary points to be diverse, to be diversity distributed along the decision between any two classes. So what we do here is that we try to try to sample maybe I'm not sorry about that. I'm not so well prepared in.
Yeah, so I think here maybe I have to interrupt it because it's already over 40 minutes.
Oh.
It's already over 40 minutes, and I think the follow-up slide is supposed to be you may not get a smoothness in the slides. So for the previous one, I think so. So can you go through a little bit about the slides?
You mean forward or backward?
Forward. Yeah, and I think for this part, you still need to spend at least 2 to 10 minutes for that, right? Or 5 minutes.
So.
Yeah, so that's based on your current speed. At least over 1 hour to finish all the slides, right? And so I just make my comment. So I assume that giving and also giving your presentations, I just feel that I'm trying very hard to make me not get to make myself focus. So my guess is that for the students, I'm not sure how many students will still focus on the slides, but first it may get lost easily. The second is that I'm not sure they have been distracted. So my guess is that some students, I'm not sure whether my guess is correct. Yufan, Changshen may get lost and they may look into this stuff. That's my guess. Yufan and Changshen can correct me if I'm wrong. And I also highly doubt that they may not be stay here, as their mind is not on the slide here. So I think the first one is that if you want to get your presentation, it's very, very important to show the work and make people interested. So so the first point is that you need to arouse the interest from the audience instead of get people to distracted. And I think even I trying very hard to focus, and even I'm trying hard, sometimes my mind is still distracted a bit by the other stuff. So that is I think that the problem of the slides here. So I just give a few points. So before I give the points, either the audience will try to give any comments based on the presentation. On Changshen and Yufan, are you still there?
Yes.
And any comments for Xianglin's presentation?
So I have two comments. First, is this slides you transferred from the Beamer? You just how did you implemented those color blocks like to approach the headlines or subtitles?
What do you mean?
You
Like
just
this?
yeah, this is a screenshot from Beamer.
No, after it is being transferred from Beamer, it looks like this. I think it got
You just
transferred to be
transform
an image.
Yeah. I think if you insist using PowerPoint, you can instead of transform from PDF to PowerPoint, you can just use a screenshot, or you simply use those softwares which can show slides of Beamer. You don't need to use PowerPoint. And the second comment is, I think if you can constantly repeat your motivation and contributions from time to time, it will be better, because the audience may forget what's your original motivation.
Can you mention what Xiangling's contribution in this work?
Yeah, contribution, because if you go into deep to the details, the audience may forget what's the original point. Yeah.
And by the way, can you, based on Xiangling's presentation, can you point out Xiangling's contributions from yourself?
It's really hard to conclude, but I think one sentence that a visualization tool is designed to give an insight for the let's say feedback or whatever. I cannot give a very precise definition. Yeah.
So you just have an impression, but you cannot pinpoint. And
Yeah.
that is up to now, because I interrupt Xiangling's presentation. It means that up until now, you just have an impression. It's very hard to form a takeaways by yourself, right?
Yeah.
And how about Yufan? Hello, Yufan there? Okay, so
I think there are too much introduction and too much background. Yeah, I hard to understand all the things.
So I think the slides still need to be improved. So if possible, we need to organize another rehearsal. I hope that the rehearsal is not need to be so. You can spend more time on the rehearsal. And here I give my comment here. So the first point is that each slide, you should not be on one slide for more than 1 or 2 minutes. So I just observed that for some slides you spend quite a lot of time to introduce it, and there's a lot of words. So in order to arouse the interest of the audience, you should not linger on a slide for more than 2 minutes. I think even 1 minute is just enough. So given a point, you just give it a point, and also you should not stuck on there. We'll go back to some slides in the previous slide. Yeah, and for these slides, and for so I think if you want to illustrate the 4 equations, you may need to use at least for 1 minute. And unless you can raise the interest, the people will just get lost. So I think in giving the presentation, the idea is just to show the rationale and intuition instead of a detailed equations. Of course, some professors can use equations because they are highly prepared and they can illustrate every detail of the equations precisely and concisely. And for now, I think in your presentations, I suggest you just use picture and graph instead of equations. And you can use equations, but your equation is just to show that we have a formalization for intuitions. And basically, we just put more the rationale that. And also, yeah, you take this rationale, you try to reconstruct your slides. If you find a slides, you need to spend more than 1 minute. You split it. At least you need to split it. And also, I agree with Changshen that we need to mention the rationale and we need to mention the rationale and why for every slice. That is, for example, I guess Changchun will be quite get lost in when have Pij log Pij over Qij, whatever it is. So people get lost in here. So why would you do that? And more importantly, it is actually the contribution of UMAP, right? So why we need to put so many efforts there? So in this case, you just show some picture, right? Since a close, it's giving 2 points. If they are close enough, we will calculate their distance. If they're larger enough, we're having some penalty, whatever. So once we have a high dimensional distance and low dimensional space, we want to have a projection, and we put all of them into an animation or a diagram. So the people, and I think for the human brain, it was much better to understand, much better at understand the picture instead of the equations. Okay, so this is anyway the first point. So when we have the equations, we try our best to replace it into a diagram. We can put the equation there, and the purpose of the equation is just to show that we have a formalization instead of we go through equation by equation, and that is what that will form a big monologue there. Okay, so maybe the next one I go to several slides and comments. Will you please go back to the slide 4?
4.
Yeah, slide 4. Yes, for these slides, I think you spent.
Oh yeah.
You can think about it for now. So when you just touch the approach, it already takes 40 minutes. So here, my suggestion is that
40 minutes. I just talk maybe 20 minutes.
No, you start at you start at 4:06 p.m.
Yeah.
And I interrupted you at 4.
Oh, okay, I see.
So
yeah,
you used at least 40 minutes.
yeah.
And you just at the middle of the approach, right? So you still have several properties to go, and you have the whole experimental part, and the whole case study part, and the final conclusion. So based if my estimation is correct, you may spend at least on 60 or to 70 minutes to go through all the slides. So that means you need to cut it half. A lot of work need to be cut. So here I just feel that these slides is still a little bit monologue. So you can either to move the example, you may just show one example. Maybe you can show one example and detail it a little bit. And for the rest example, just to mention it instead of go one example by the other. And if you go example, I suggest that you prepare another separate slides to tell about adversary training. And yeah, and also for here, it means the mislabeled data. And the mislabeled data is the reason, right? It's usually the root cause. It is possible to the observation. If we already observe there's mislabeled data, we already address the problem. So in this case, if you want to go with another example, also I suggest that you talk about the phenomena, right? For example, the training, the loss decrease very hard. The loss decrease in a very hard way, and it means that the model is learning slowly. And what is the reason? Maybe it is the reason of mislabeled data, right? So this is slide 4, and the next is slide 5. And the slide 5, I guess you spend too much. You also spend too much time on the related work. So again, you should not spend more than 1 or 2 minutes here. I think you can just briefly mention the gradient, integral gradient, and gradient, because gradient has a picture. It's good for people to follow, and maybe 30 minutes for all that work, and another 30 minutes is for the deep view. And here, once we have the deep view, we need to criticize a bit. For example, so for this classification landscape, it doesn't have a classification landscape, and what is the limits, right? For example, it is very slow, and also it cannot shoot in the spatial temporal quality, right? So just within 1 minute, and this slide should be gone, right? And also I observed that you use a word. I think you always use the word you, right? You will say, you cannot now, something like that, talking about the audience. So a more professional way, you're talking about we. So you're using we, so it makes you make you and the audience closer, right? You say we have approach, right? It seems that the author is one of us, so it makes the people feel closer.
Okay.
And then would you please go back to the slides 11. 11. Yeah, here we have already reached the solution, right? It's not example. So my suggestion is that we put it here. You highlight it in a very clear way, saying that it is our solution, DVI, and then where the source code. You can just mention it here. So in this case, you should, because it's now comes into our contribution, and also this is a way. So this example is a way to show how we pinpoint the root cause, right? And how do we track the root cause? The reason is that given a point, given the testing data, and after we apply the virtual training on the model, the testing data is screwed and it loses its accuracy. And why? And then the reason is that we find that a lot of these neighbors are the virtual neighbors. So basically, you can illustrate the red point. Because I feel that you rely a lot on your oral explanation, right? You use your oral explanation trying to explain everything. But one thing you need to know that even the professors, they will get distracted. So when you show the presentation to Prof. Gong, you will find that sometimes you were asking, and even you will present to me, you will feel that when we have the group meetings, even I will repetitively ask a similar questions, right? So you mentioned this before, but after several slides, my memory get fading. Especially, I'm not getting excited when explaining some point in previous slides. So I will ask the point you mentioned before. So I think this is not a problem of individual people. I think that's problems of all the human beings. So that still align with Changshen's concern that we need to duplicate information across the presentation. For example, when we reach here, right? So people will ask what is the point means, and what is neighbor means, and what is classification, etc. So in this case, you may have some annotation saying that the big node is actually a testing sample, right? And the rest nodes is actually the reverse race, and they move together. So here we still need to have more detailed annotation, and the idea is to replicate information. And also another suggestion is that before you go through this specific reason, because this specific reason is about several samples. Before you're giving the examples, I also suggest you give an example training. So you give an animation training. So when doing the training, the classification landscape is evolving, and the location of the samples is evolving. And it's started with classification landscape. Everything is randomly scattered everywhere. And after the trainings, the classification the classification landscape or boundaries becomes more and more clear, and the samples are more concentrated on certain regions. So we just first show such a picture, and after we show such a picture, then people will say, "Oh, that's interesting." Then people will ask another question like, "So what? Now we have something interesting, but how it can improve the usability and how it can benefit us?" So this will be second question. So in this case, we introduce this question. We introduce these samples. So in brief, we start with animation, which seems interesting, and then we followed up with animation, which shows usefulness, right? So these two, and based on these two examples, we can to make the slides more convincing. Okay, so that is my comments on slide 11, and also can you go forward to slide 20? Yeah, and also you try to read, right? So basically, read. So that is, yeah. Once you read the words, it makes you smooth, make your speech smooth, you will not have a lot of the some kind of the interpretation. But the problem of reading the text makes you less emotional. Right? So people will I cannot feel you're excited with your work. Or anyway, I suggest like that you it's better when you show something to the audience. It's better to let people feel at home. You are talking gossip with some people, saying that, and so your expression will be very smooth, and your tones will be very friendly, and you share the interest. So it's better to have such effect. So when everything is planned, but anyway, that is the first step. You get yourself smooth, and also I suggest to make sure that your words on each slide should not be too many, so that you can control if you find you cannot use less word, you try to split the slides instead of and now let's go back. Here is the slide 20, right? So slide 20, you want to show the importance of why the boundary. And if it is for important boundaries, I also suggest that you replace the active learning. And you either to move learning to another slide, or you just showing that in what scenarios, you just still show a picture. In what scenarios we need to find the points on the boundary. Right, just use a picture. And also I'm not sure this is 100% correct, but for now, maybe you can use some rules that in one slide, you should not use words more than 20 words, or use more than 30 words. If the words is more than 30, we exchange the words into a picture or diagram. Because people can accept the diagram much faster and in a more efficient, much more efficiently than they read the text, right? And then we go to 22. Yeah, 22. Yeah, let me think about. This is temporal preserving. Let me think about it. So here, yeah, I think we discussed it before, right? So it's better to provide a DVI instead of UMAP, and also the random the better. The random the better. This is still the property, right? We haven't touched the approach. This is talking about the property. So if it is the property, I suggest we find it, and also for this equation, I think these equations, especially expected that it is in the paper, and the reviewer will have spent time to digest. Otherwise, you just based on your oral presentation, it is really hard to follow. So I also suggest that if you want to keep this equation, that'll be fine. But you have to provide it with some animation graph. And this graph, you can drop this graph. There's no need to use our tool to generate the graph. You can just draw some graph and show the idea. And that is all, right? And I think you first have a slice. You try to shrink the slice. But if the slice is the number of slices is increased based on animation, that is fine, because if you go through with animation, animation means that they have consecutive similar slides, which just show the animation. So that'll be fine, because these slides can be just considered as one slice, and the presentation showing the animation only requires maybe a few seconds. So that'll be fine. Otherwise, once the slide for the slide which takes more than 1 minute, we need to shrink it. Yeah, okay, so that is basically what we have. What I have for improving the QE presentation. Okay, so is there anyone have the questions for Xianglin's presentation?
Hi, Junbo here.
Okay, Junbo.
Yeah. I heard like when during the previous presentation, right? I know how Xianglin speaks, but for this time, at the very beginning, I can feel that she's very stressed, and so far this is just presenting to us. Then if if she present to prof, I think she will be more nervous. Also, we need to.
I think the here is I think the confidence lies in the preparation, how prepared you are. I think Xianglin can feel that he is not well prepared. He's still trying to cope with the world here. So in this case, since he understands she is not that prepared, so the confidence will be compromised and undermined. So I suggest you. So usually when I gave my first conference presentations that was in 2014, so it's quite a year. So I recite every word. I recite every word. So it's more like based on my experience, it's more like acting, right? So at that time, you are only a PhD. There's a lot of audience, which is very senior professors. So it is very natural that we cannot gain the confidence. But the point is that if you're acting as a confident student, then you will get your atmosphere changed. So in this case, I suggested first you need to Xianglin need to fully prepare the slides and make sure that from your side, and you have already done your personal best. And also, but when after you achieve these, you should know that in this world you are the only one or only few people know the approach exactly. And for Xianglin, you know exactly every line of code to implement this. So you should have the confidence. And also, if you do not have that confidence, you act like confident, and that will be great. Yeah. Thanks, Jingbo's.
Thanks.
Okay, so I think
I want to ask one more question. So at first point, you mentioned that I need to, like for each slide, I need to mention the rationale, but how is that possible? Like,
no. So I'm not saying that. I think you need to recap the information required to understand the slides.
Okay.
So of course there's no need to rationale. And I think the point Changshen raised is that when you go to maybe I guess about 20 minutes during the presentation, maybe I think you spend too much time on the background. So as long as I think the background is good, as long as people can know what they're doing, right?
Okay.
And also sometimes, especially it is a very intensive and a very solid work, and people will struggling to understand what really is, instead of questioning, is there any related background? And also, I guess a lot of professors in communities may not have very strong background to say whether this is novel or not. So in this case, what they want to do is they're trying to learn. They want to trying to learn and grasp as much as possible. So in this case, you need to satisfy their needs instead of including everything. Presentation is just to give people the novelty instead of giving people a comprehensive bunch of knowledge. And I think a lot, especially when people getting older, even for me, when I host the 2 presentation and when it goes to yours, I almost get a little bit tired. So in this case, what I want to have is that I want to get information. I want to get the information I'm interested as soon as possible. Then I can grasp it. But when you folks give me a bunch of knowledges, even if the knowledges, that is knowledge I know, I will still soon, it will also soon exhaust my limited energy there. Okay, so that is basic comments I have. So there's still a long way to go to prepare the slides. So let me summarize and recap. Yufan, Changshen, and the comment Yuchen, Changshen, Jingbo, and I. So the point is that you do not be nervous, but which means that you need to be well prepared. The second is that to avoid the monologue. So Changshen mentioned that he get lost from time to time. So it means that you spend too much time on, so their memory or their limited memory resources is exhausted. Try to keep the audience, keep the limited memory resources of the audience, because the audience can only remember only a few stuff, especially they are not an expert or professionals. And my comments is that for each slide, it should not last more than 1 or 2 minutes. That is aligned with Changshen and Yufan's points. And also to replace the equations and the words with diagram and graphics, animation, as many possibles. And there's no need on put too much time on the related work. Yeah, that's all from my side.
Okay.
Okay, is there any other questions or comments for Xianglin? Okay, if there's no comments, let's call it a day. Thanks everyone for sharing the presentations, and thanks Xianglin for preparing. But there's still
I will enhance my QE slides and send you the revised version later.
So maybe you can. So I will not push you too much this time. But I think if I not push you, you do not have not those many versions. How about this? Before Monday, you provide a version. And how about that?
Okay.
Okay. Thanks everyone. Let's go today. Bye.